Ok, benvenuti all'ennesimo seminario di analisi complessa. Oggi Pavel Gumenyuk, spero di aver pronunciato bene, ci parla di Quasi-Conformal extendibility of holomorphic functions and Becker's construction.
Okay, thank you very much. I'm very grateful to the organizers for invitation to give a talk at this online seminar. It's a pleasure and honor and a new experience for me. So I hope that everything would work fine. So I tried to prepare a talk for a general audience. And that is why probably 2/3 of the talk are just known things. So let us start with the quasi-conformal mappings. They serve as a natural extension for a notion of a conformal mapping. For example, in the space, in the dimension greater than 2, there are very few conformal mappings, but there are plenty of quasi-conformal mappings. However, in this talk, I will only work with quasi-conformal mappings of plane domains. Already in the dimension 2, there is a rich theory of quasi-conformal mappings, and they have many applications. And if you attended the talk of Jasmine Racy, you of course heard about one of them, quasi-conformal surgery in complex dynamics. So here there is a definition. So we consider a plane domain D and fix a number k, non-negative number, strictly less than 1. A k quasi-conformal mapping of the domain D is a sense-preserving homomorphism of this domain onto its image, having locally square integrable partials of the first order understood in the distributional sense. So that's these words are basically encoded in this notation. And solving the so-called Beltrami partial differential equation, so in which this function mu is a measurable function with L infinity norm not exceeding k, and this d bar and d are just standard notations for formal partial derivatives with respect to z and z bar. Oh, I forgot to tell you that please feel free to stop to interrupt me and ask questions whenever they appear, because maybe certain things will not be so clear. Well, for almost everywhere in this domain, a quasi-conformal mapping F is differentiable, and moreover, at almost every point, the differential is different from zero, from trivial map, and moreover, it maps circles onto ellipsi with bounded ratio between the semi-axes. So this bound, upper bound for the ratio k capital, is related to k small by a very simple relation. So at the beginning, in the definition I wrote in k small notation. What does it mean, k small notation? Many specialists in quasi-conformal mappings, they prefer to use this parameter k capital. So they say a k quasi-conformal mapping if basically if the ratio between the semi-axis of this infinitesimal ellipsi is less or equal than k. While other specialists prefer to use this k small as a parameter. So I use k small. Well, there is one more elementary thing to mention, is that if k capital equals 1 or equivalently k small equals 0, then these infinitesimal ellipsi are just circles, and moreover in the Beltrami equation we have it becomes d bar f equals 0 in the right hand side. So 0 k quasi-conformal mappings are just conformal mappings. In this sense, they are that's an extension of the notion of conformal mapping. Well, since quasi-conformality is invariant with respect to pre and post compositions with conformal mappings, the above definition extends naturally to Riemann surfaces, in particular to the Riemann sphere. Of course, in general, Riemann surfaces, instead of Beltrami coefficient, instead of this function, we should look at a particular type of tensor. Yeah, so sometimes called Beltrami differential. However, for the complex sphere, it's enough to basically consider this equation on the complex plane. Well, for the complex sphere, one of the most important results in the theory of quasi-conformal mappings is the so-called Riemann measurable Riemann mapping theorem. But this thing is also always hard. I don't know where to put this thing. Well, this theory says the following. Consider any Beltrami coefficient mu in the whole complex plane. By Beltrami coefficient mu, I mean an element of the unit ball of the space L infinity. So this subscript 1 exactly means that we are considering open unit ball. So for any Beltrami coefficient in the plane, there exists a quasi-conformal mapping of the sphere into itself, satisfying the Beltrami coefficient with this mu. Moreover, this map F is a homomorphism of the sphere into itself, is just by a topological reason. It has nothing to do actually with the quasi-conformal mappings. And it is determined by the Beltrami coefficient mu uniquely up to post compositions with Möbius transformations of the sphere. So if, for example, we impose some normalization, let's say give certain values at 3 different points of the sphere, then there exists exactly one solution to the Beltrami equation in the sphere, satisfying this normalization condition. Homomorphic solution, of course. We are talking about homomorphic solutions. If we consider this partial differential equation in general, there are plenty of other solutions. So up to a Möbius transformation, Beltrami coefficient determines a unique quasi-conformal mapping of the sphere. And one of the curious and useful corollaries of this theorem is that every Beltrami coefficient, even if we consider some domain, not necessarily a sphere, and this also works for Riemann surfaces. So every Beltrami coefficient defines a new complex structure, so on its domain. And with respect to this new complex structure, the homeomorphic solutions to the Beltrami equation, they are conformal. So you can think about quasi-conformal mappings as deformations of the conformal structure, and these deformations, they are actually encoded by Beltrami coefficients. Okay, but what about the Beltrami equation in a domain different from the whole complex sphere? For example, for the unit disk. Well, in this case, in the case of the unit disk, life is quite simple. By result of Mori, quite old result, every quasi-conformal automorphism of the unit disk D extends homeomorphically to the boundary, and hence it can be extended to a quasi-conformal mapping of this sphere by this formula, basically using the reflection with respect to the unit circle. And this the Beltrami The Beltrami coefficient of this extension satisfies this simple symmetry property. So basically, this is how the Beltrami, more or less, this is how the Beltrami coefficient changes under change of coordinates. On the other hand, if we consider any quasi-conformal mapping solving the Beltrami partial differential equation satisfying this condition, then using the symmetry with respect to reflection with respect to the unit circle, we can obtain another solution. In principle, if the f is properly normalized, suitably normalized, they can coincide. But f star is also a solution of the Beltrami equation with the same mu. It is just because we suppose that mu satisfies this symmetry condition. So taking into account these observations, one can say that by the measurable Riemann mapping theorem, to every Beltrami coefficient mu in the unit disk, there corresponds a quasi-conformal automorphism of the unit disk defined uniquely up to Möbius transformations of the unit disk. So post-composition with the Möbius transformations. So also for the unit disk, this is true. Given a Beltrami coefficient, we can find a quasi-conformal automorphism of the unit disk, which is defined by this Beltrami coefficient up to post-composition with the Möbius automorphism of the unit disk. So basically the same was here on the previous slide for the sphere. Well, by certain reason, further on, it would be more suitable for us to work with quasi-conformal automorphisms of the exterior of the unit disk, but this does not change anything, basically. So similarly to every Beltrami coefficient in the exterior of the unit disk, so D star is the exterior of the unit disk, to every such Beltrami coefficient, they correspond to unique quasi-conformal automorphism of the exterior of the unit disk, which I would normalize by requiring that it fixes one point inside the exterior, infinity, for example, and that it fixes one point on the boundary, this point 1. So this, in such a way, we avoid we just fix one solution. We avoid this possibility to post-compose with Möbius transformations. Well, how do we obtain this quasi-conformal automorphism? We consider the Beltrami equation in the whole sphere with the normalization that infinity, 1 and 0 are fixed. The coefficient mu here, mu1, the Beltrami coefficient, is obtained by extending mu symmetrically to the unit disk. We use symmetry with respect to the unit circle. And then the last step is just to take a restriction of this U capital to the exterior of the unit disk. And this restriction is the required, desired automorphism of the exterior of the unit disk. But at the same time, starting with the same Beltrami coefficient in the exterior of the unit disk, we can obtain a conformal mapping of the unit disk uniquely determined by this coefficient in the following way. Instead of extending, like here, the Beltrami coefficient by symmetry, we extend it simply by 0. So we solve the Beltrami equation in this sphere, taking mu as it is in the exterior of the unit disk and taking 0 inside the unit disk. Then the corresponding automorphism of this sphere F capital will be conformal in the unit disk, so we can choose a little bit different normalization to have uniqueness. So we require that it fixes infinity, that it fixes 0, and that the derivative at the origin equals 1. So here I can write the derivative, of course, as a complex derivative or as a partial derivative with respect to z. So, and then if we restrict this map to the unit disk, we obtain a conformal mapping of the unit disk, which is tangent to the identity at the origin. This is a standard normalization for conformal mappings in the unit disk, which is usually considered in the geometric function theory. Right, so we obtain certain elements from the so-called class S. The class S is the class of all conformal mappings of the unit disk normalized in this way at the origin. Of course, not every element of the class S can be obtained in this way. Exactly, we obtain those elements which admit quasi-conformal extensions to the sphere. So let us summarize. So, to any Beltrami coefficient in the exterior of the unit disk, they correspond in a one-to-one manner a quasi-conformal automorphism of the exterior of the unit disk with this normalization. At the same time, there is one-to-one correspondence with the quasi-conformal automorphism of the sphere fixing infinity and 0, and which are conformal in the unit disk and additionally normalized by the condition that the derivative at 0 equals 1. So here actually I saved some space. I have not written that f of infinity equals infinity. However, this is already included here, because if we consider any quasi-conformal mapping of the plane into itself, then it is actually an automorphism of the complex plane, and it also can be considered as automorphism of the complex sphere fixing infinity. In this sense, quasi-conformal mappings are very similar to conformal mappings, because conformal mappings of the plane, they are just linear functions, and so they are onto and they represent automorphism of the sphere fixing infinity. Okay, but now if we remove part of the information, if we forget about values of f capital outside of the unit disk and just restrict to its conformal part, to the unit disk, so then we obtain a quasi-conformally extendable element of the class S, and of course we lose information. So this map is not injective, fibers are huge. Unfortunately, there is no good, at least up to my best knowledge, there is no good analytic description of fibers in terms of these Beltrami coefficients, but in terms of the corresponding quasi-conformal automorphisms of the exterior of the unit disk, such a description exists. Actually, restricting f capital to the unit disk is equivalent to restricting the automorphism to the boundary. So, as I already mentioned, the automorphism of the unit disk, quasi-conformal automorphism of the unit disk or of the exterior of the unit disk can be extended homeomorphically to the closure. And now we get the we take the restriction. So what kind of homeomorphisms of the unit circle we get? This is a very well-known result. In fact, a sense-preserving homeomorphism of the unit circle onto itself extends to a quasi-conformal automorphism of the unit disk or exterior of the unit disk, if and only if this quasi-symmetry property is satisfied. So what do we do here? We take an arbitrary point on the unit circle, let's say zeta, and then we step in the clockwise direction and in the counterclockwise direction by the same angle, let's say theta. So here theta can be both negative and positive. And then you consider the ratio of the distances, right? The ratio of the absolute values of increments of our map gamma. So if this ratio is bounded and by a constant which does not depend on the point, so the constant should be common for all points on the unit circle and for all values of delta, then this homeomorphism is said to be quasi-symmetric. So the boundary values of quasi-conformal automorphisms are exactly sense-preserving quasi-symmetric homeomorphisms of the unit circle. And in fact, we get a one-to-one correspondence between quasi-conformally extendable conformal mappings normalized at the origin on this part and these quasi-symmetric mappings here. This one-to-one correspondence can be made more explicit by means of the so-called conformal welding. So what we do here, we take our function f, it maps the unit disk onto a Jordan domain. So then we can equally consider a conformal mapping G of the exterior of the unit disk onto the exterior of that domain. To have uniqueness, we can normalize it. For example, infinity goes to infinity, and then we ask for one point on the boundary to be fixed in the sense that f and g have the same value. So both mappings extend homeomorphically to the unit circle, hence this composition of f with the inverse of g is a homeomorphism of the unit circle. Well, here I always keep track on fixing the point 1 on the unit circle. That is why we have this normalization. So in fact, in the category of quasi-conformally extendable univalent functions and quasi-symmetric homeomorphisms of the unit circle, this correspondence is essentially one-to-one. With the normalizations we have, it's actually one-to-one. Yes. Well, maybe it's worth to mention that, in fact, conformal welding can be considered for any conformal mapping onto a Jordan domain, right? And this is on the left side, and on the right side, we can say, let us consider an arbitrary homeomorphism. Sense-preserving homeomorphism, of course, of the unit circle, but in this most general context, unfortunately, conformal welding, understood as this map which takes f to gamma, this mapping is neither surjective nor injective. However, when we live in the quasi-conformal world, the map is bijective. So let us now forget for a moment about quasi-conformal mappings and just concentrate on conformal mappings of the unit disk. Let us recall that the class S is the class of all such conformal mappings with the normalization at the origin. Yes, so what we have seen is that the subclass of the class S formed by all conformal mappings normalized at the origin and admitting quasi-conformal extensions to the complex plane, it has a natural one-to-one correspondence with this interesting object. So it's a group of all sense-preserving homeomorphisms, quasi-symmetric, sorry. So all sense-preserving quasi-symmetric homeomorphisms of the unit circle modular the rotation group. Why do we have here the modular? Because of this condition, right? So fixing one point means that we do not consider an arbitrary homeomorphism, but up to rotation. Well, this from the point of view of complex analysis, this nice object is a natural extension of the so-called Kirillov's homogeneous manifold. This manifold is the group of sense-preserving diffeomorphisms of the unit circle modular the rotation group. So there are many things about this object which makes it interesting to specialists, for example, in representation theory. So it has a natural complex structure defined by, generated by the Hilbert transform, for example. Yes, well, but from the point of view of complex analysis, actually, diffeomorphisms are not so good. So we should actually consider a larger set. Well, there is also a connection with the so-called universal Teichmüller space. So if instead of taking a quotient modular rotations, we take quotient modular all Möbius transformations of the unit disk, then we obtain one of the realizations of the so-called Teichmüller space. And in fact, the Teichmüller space can be identified with the set of all Schwarzian derivatives. So we start with this class of quasi-conformally extendable univalent functions normalized at the origin. Then we take the Schwarzian derivatives. Then we obtain that certain identification happens, and we obtain a very natural realization of the Teichmüller space. This is called, by the way, this set of holomorphic functions is a bounded domain in a certain Banach space of holomorphic functions. This is called the Beer's embedding of the Teichmüller space. So I pronounce these words universal Teichmüller space without mentioning what it is. Well, unfortunately, in one talk it's not possible to explain everything. I just would mention that the Teichmüller space of the unit disk is called the universal Teichmüller space because it contains Teichmüller spaces of all hyperbolic Riemann surfaces for which the universal cover is conformally equivalent to the unit disk. And well, then I should probably say something about the Teichmüller space of a given Riemann surface. I would just restrict to the case of compact Riemann surface. And in this case, the Teichmüller space of this Riemann surface is a sort of moduli space of all Riemann surfaces quasi-conformally homeomorphic to the given one. So to give an idea what is the difference between simply two homeomorphic Riemann surfaces and quasi-conformally homeomorphic Riemann surfaces, I give an example of non-compact, in a non-compact case. Consider an annulus with both boundary components being circles and another annulus with a different ratio between the radii. They are quasi-conformally equivalent. However, if one of the boundary components is just one point, for example, it's a punctured disk, or the whole complex plane minus a disk, closed disk, then there is no quasi-conformal homeomorphism between such a domain and an analysis with both boundary components being circles. Well, all in all, we can say that quasi-conformal extendable conformal mappings is an object which appears very naturally in the theory of quasi-conformal mappings. So it's not just artificial construction. That's an object which is interesting to study. Well, if now for a moment we forget about quasi-conformal extensions and just think about the class S, then one of the most effective tools to study this class is the following fact. It is known as a parametric representation of univariant functions, and it can be stated as follows. The class S is the range of this map. Well, this still does not define map. What is P? So what is the object the map applied to? Is P is a so-called Herglotz function. So in this setting, Herglotz function is defined as follows. So it's a function of two variables, one of which is complex variable z ranging in the unit disk, and the other variable t is a real variable with non-negative values. So with respect to the variable t, this function is required to be measurable. With respect to the variable z, it is required to be holomorphic, and is a holomorphic function with non-negative real part. And then we need some certain conditions on behavior of this function at z equals 0 as a function of t. So it is required that p of 1 is locally integrable, but its real part is not globally integrable. So the integral from 0 to plus infinity of the real part equals plus infinity. Well, yes, how this P Herglotz function is related to this limit, to this function phi 0t. These functions phi 0t are holomorphic self-maps of the unit disk defined as unique solutions to the following initial value problem for the equation. Yes, now it appears. So this equation is known as the Löwner-Hofer ODE. So then this z is considered as a parameter, so it's basically initial value. T is considered as a variable, and the first subscript 0 reflects the fact that the initial condition is given at t equals 0. The initial condition is the identity map. Well, so for any Herglotz function, this initial value problem defines uniquely a family of self-maps of the unit disk, holomorphic self-maps, univalent. And then if all of these maps, they all fix the origin. And if we also renormalize them in such a way that this guy is always in the class S, then the limit exists and it is a function from the class S. And the main point here is that every univalent function, every element of the class S can be written in this form. Well, this map, which takes a Herglotz function to the corresponding normalized univalent function, is not injective, of course. However, it is a natural problem to find a class of Hilbert's functions whose image coincides with the given subclass of S. So we consider a subclass of the class S and then want to find a class of Hilbert's functions which generates the given subclass of the class S. For example, a trivial, well, not that trivial, but a simple example is the class of all star-like mappings, conformal mappings onto domain star-like with respect to the origin. This class is generated by Hilbert's functions, which do not depend on T. So if here P depends only on Z. Well, somewhat more complicated and more related to the topic of the talk is a result by Becker. So he gave a partial answer to this question for the subclass formed by functions admitting quasi-conformal extensions to the plane. So this is the theory. Fix some non-negative k strictly less than 1 and suppose that we have a Hilbert's function that satisfies for almost every t, it satisfies this condition, that the values lie in this closed disk. So this, of course, a Euclidean disk, but we can also describe it as the hyperbolic disk in the right half plane H, centered at W equals 1 and of radius 1/2 of the logarithm of k capital. So when k small tends to 1, then k capital tends to infinity, so the radius tends to infinity. This set U, this disk, expands to the whole right half plane. Well, for finite k is just a compact subset of the half plane, and if this condition, which I call Becker's condition, if this condition holds, then the corresponding element of the class S admits a k quasi-conformal extension to the plane, fixing infinity. And in fact, we can write down the formula for this extension. So for Z outside of the unit disk, it is given by boundary values of a certain family of holomorphic functions. This family Fs is the so-called Loevner chain associated with the Hilbert's function P. So how can we construct this Loevner chain? Well, this Loevner chain, the elements of this Loevner chain can be expressed in a way quite similar to how the function f is obtained having fixed a Hilbert's function p. So the difference is that now we have to consider two-parametric family of self-maps. Yes, so these phi st are holomorphic self-maps of the unit disk, which are defined by the initial value problem for the Loevner-Kufarev equation, and this S, the first subscript, is actually defines the point of time at which the initial condition is placed. So in this case, the initial condition is given at the point t equals S. So this can be taken as a definition of the Loevner chain associated with the Hilbert's function P. Well, there is also an intrinsic definition, but before I would like to cite some properties of this Loevner chain. First of all these functions Fs are univalent in the unit disk. Then for any t greater or equal than S and S non-negative, this functional equation is satisfied, and in particular it follows that the image domains form an expanding family. So if the image of Fs is contained in the image of Ft when T is greater or equal than S. Finally, it is also known that the Loevner chain satisfies the Loevner-Kufrieff partial differential equation. Well, and in fact, looking to the partial differential equation and this ordering differential equation, and plus this functional equation, we can notice that the family phi st can be interpreted as a family of characteristic curves for this PD. Okay, so let me now give an intrinsic definition for, so we are talking about, let's say, classical setting. And in this classical setting, a family Ft is a Loevner chain in the sense of Becker if all the elements are univalent, meaning injective and holomorphic, then the image domains are increasing or expanding family of domains, and there is this normalization that every function Ft fixes the origin, then the function which takes T to the derivative of Ft is 0 is locally absolutely continuous. And moreover, it is supposed that its absolute value goes to infinity as T tends to plus infinity. The very last condition, this condition is equivalent to saying that the image domains, that they are union. The union of all image domains is the whole complex plane. So that's an intrinsic definition, and in fact, there is a one-to-one correspondence between Loevner chains and Herglotz functions. So every Herglotz function generates a Loevner chain by a procedure which I showed before, and at the same time, every Loevner chains, in the sense of this definition, corresponds to a unique Herglotz function. You can basically do the following. You can take this partial differential equation and express the function P here. Well, let us now define a so-called Becker extension. That's basically extension which we obtain using Becker's result. Well, we say that a homomorphic extension of a function f small is called a Becker extension if it is quasi-conformal and if it is given by a Loevner chain in the following sense. There exists a Loevner chain Ft with continuous extensions to the unit circle. So every element admits a continuous extension, and those continuous extensions define the values of f capital on concentric circles. So the values of f on the circle of radius e to the power t are just boundary values of the function ft. In such a case, we say that f capital is a Becker extension of the function f small, and that ft is a Loevner chain associated with this Becker extension. Well, is it interesting to study those Becker extensions? Yes, the result of Becker is very curious. It connects to quite different things: the Loevner theory, the parametric representation, and quasi-conformal extensions. Well, that is why in a recent paper, joint paper with Istvan Prause, we obtained the following characterization of Becker extensions. So consider a quasi-conformally extendable univalent function and let f capital be its extension. Well, then denote by mu f its Beltrami coefficient. F is a Becker extension if and only if the Beltrami coefficient of F satisfies the following condition. On almost every concentric circle, the Fourier coefficients of mu f vanish for all n less than 2. So all negative Fourier coefficients are zeros. C naught is 0 and Cn is 0. This is equivalent to the possibility to extend mu from this circle holomorphically in the disk bounded by the circle. And moreover, this holomorphic extension has a 0 of order at least 2 at the origin. Well, the second part of this theorem allows to find the Herglotz function of the Loebner chain associated with the Becker extension. So if this condition is satisfied and hence F is a Becker extension, then we can, for almost every t, we can construct this function. So what we do, we consider the holomorphic extension of mu from the circle rho of radius rho equals e to the power t. Then we divide it by z square, and then we replant this function to the unit disk. So all these functions psi t are holomorphic functions in the unit disk. And then with the help of Cayley transform, we obtain a function with positive real part. And this function is exactly the Herglotz function of the Loebner chain associated with the Becker extension F. Yes, and of course, this function P satisfies the Becker condition because the function psi is bounded, the absolute value of psi is bounded by the L infinity norm of the Beltrami coefficient. So one corollary, which I think was quite clear for many specialists, but I have never seen it written and proved. One corollary is that the class of all functions in S that admit a Becker K quasi-conformal extension. So here we fix the norm, or better to say upper bound for the L infinity norm of the Beltrami coefficient. So we call this class SKB. So this class is a proper subset of the class of the subclass of the class S, which is formed by all elements admitting K quasi-conformal extensions with the fixed point at the infinity. So this class is strictly less. Although this is a proper subclass, so with the Becker construction, we do not obtain all elements of SK. His result deserves further investigation. So, and then now I will try to give several reasons for that. Probably the most well-known reason is that many classical sufficient conditions for quasi-conformal extendability can be deduced from Becker's condition. I said many. There are not so many, but most of them can be deduced from Becker's result. Here I give just 2 examples. So if we fix this parameter k, consider a holomorphic function in the unit disk. For simplicity, we suppose that it's normalized as functions in the class S. Then this simple condition on the pre-Schwarzian derivative of f, if this inequality is satisfied at every point of the unit disk, then our function f admits a quasi-conformal extension, and moreover, it admits a Becker K quasi-conformal extension. So it belongs to this smaller class S KB. So another sufficient condition uses the Schwarzschild derivative. So if somewhat similar inequality holds at all points of the unit disk, then F admits a K quasi-conformal extension to the sphere, but in general it is not guaranteed that the infinity is the fixed point. It's if and only if the second Taylor coefficient here is 0. Well, anyways, so this function, a function f satisfying this condition, does not need to belong to this class. However, the extension here can be obtained with the help of Becker's construction. Well, another reason, in some cases, Becker's extension appears to be the best one. That's one of the results in a joint paper with Ike Hota, which is going to appear in Proceedings of the American Mathematical Society. So again, we fix K. We don't consider the trivial case when K equals 0. We take a finite number of points in the unit disk. Some of them even can coincide. And then consider this simple rational function. And this rational function gives rise to a Beltrami coefficient in the exterior of the unit disk given by this formula. So this form is somewhat classically known in the theory of quasi-conformal mappings, the so-called Teichmüller map. So it's a quasi-conformal map with the Beltrami coefficient of this form. Well, but phi is exactly of this form in our case, and if this Beltrami coefficient now, it generates a K quasi-conformally extendable function f and its extension f capital. So for this Beltrami coefficient, we prove that f capital is a Becker extension. And moreover, there are no other K quasi-conformal extensions of F fixing infinity. So, of course, there are plenty other quasi-conformal extensions, but all of them, except for F, for this one, all of them, they have a Beltrami coefficient with the L infinity norm strictly greater than K. So, in this sense, the Becker extension F is the best one, is the optimal one. So there is a quite large family of examples in which Becker extension appears to be the optimal one. Well, yet another reason. If our function f has a K quasi-conformal extension, that is, it belongs to Sk, with K sufficiently small, then the function f admits also a Becker extension. In fact, it is easy to show that this is the case for K less than 1/6. Then for K less than 1/6, Sk is a subset of SB6K. So every K quasi-conformally extendable every function K quasi-conformally extendable to the plane admits also a Becker quasi-conformal extension, but with a constant 6K on place of K. In fact, this 1/6 can be improved in a sense. That's a theorem, main result from for all K less than 1/3, there is a non-negative number less than 1, such that every K quasi-conformally extendable function is actually a Becker quasi-conformally extendable with a Q of K on place on the constant K. So unfortunately, the method which I found does not allow to write down any nice formula for Q, but for sure it exists. Well, I do not know whether this constant is best possible 1/3 or this result can be proved. Well, I have even more reasons why Becker extensions are interesting. Becker condition survives in the general setting, in the general intrinsic Loevner theory suggested or introduced by Filippo Bracci, Santiago Diaz Madrigal, and Manuel Contreras. So to explain just in a few words, I would say the following. Explain what does it mean, this general setting. I would say the following. We have seen the Loevner-Koforev ordinary differential equation. It can be generalized. So in the right-hand side, we place a function g of this form. So if we neglect for a moment dependence on t and think about tau as just a point in the closed unit disk, then g becomes, then this formula becomes a famous representation formula due to Bergson and Porta for infinitesimal generators of one-parameter semigroups. One-parameter semigroups of holomorphic self-maps of the unit disk. Well, here, if now you ask me what's about the dependence on time, everything is measurable, first of all. So tau is an arbitrary measurable function with values in the closed unit disk. P depends on t in a measurable way, and as a function of z, it's still a holomorphic function with no negative real part. Well, of course, there is a certain integrability condition, local integrability condition, which is necessary to make perfect sense of this initial value problem and to assure that the solution exists, it is unique, and it's holomorphic with respect to z. Well, for any function p and for any function tau satisfying pronounced and not explicitly pronounced conditions, we get a two-parametric family of holomorphic self-maps of the unit disk, and the classical case, by the way, corresponds to tau equals identically 0, in which case here we simply get minus z p of zt on place of g. Well, when I say that Becker's condition survives in a general setting, it means exactly the following. The theorem actually was proved independently by me and Istvan Prause. The paper is published already in 2019, and by completely different method by Ike Hota, and his paper is to be published in Journal d'Analyse Mathématique. So the theorem says that if P satisfies Becker's condition, regardless of the behavior of this function tau, all these mappings phi st defined by the generalized Loevner-Koforev ordinary differential equation, they all admit quasi-conformal extensions to the sphere. Then you may ask me about the Loevner chain. Yes, first of all, how do we define corresponding Loevner chain? One way is just to say that we look for a family of univariant functions with parameterized by non-negative t, satisfying this functional equation. So it is known that such a family always exists, and in this case, when Becker's condition is satisfied, it's actually unique up to compositions with linear mappings of the plane. And what the theory states is that also all the elements of this Loevner chain, they admit quasi-conformal extensions to the sphere, but neither in this case nor in this case in both cases we do not have information about infinity. So infinity is not necessarily fixed in this setting. Well, there is the classical case is a special case when tau equals 0, right? But there is another interesting case when tau is always 1. This is somewhat called the Chordal Case in Loevner theory, and Becker's construction, or better to say, its analog for the Chordal Case. It can be used to obtain new sufficient conditions for quasi-conformal extendability, and it's actually easier to work with functions holomorphic in the right half plane. So one very nice sufficient condition for a function h in the right half plane to have a k quasi-conformal extension to the whole plane is the following. So here it's again in terms of the pre-Schwarzer derivative. Well, I was very glad when we discovered this condition, but then I discovered that it was already obtained in 1984 by Becker and Pomerenke. Well, there is another sufficient condition which, up to my best knowledge, is completely new. So if for some positive constant alpha and the real constant beta, h satisfies this condition, then h admits a quasi-conformal extension to the whole plane. More precisely, this condition star implies that h has an angular derivative at infinity with the limit where the limit can be taken also unrestricted. It has a continuous extension to the imaginary axis, to the boundary of the right half plane, and using this continuous extension, we can write its quasi-conformal extension. So here I gave this formula. Well, it's probably not to see all the details of the formula. Yes. Yes, it's not very interesting to see all the details of the formula, but there is one. Sorry, I do not know why these sounds start to appear from my mobile phone. Yes, so one interesting feature which doesn't appear in the for the classical Becker's construction is that this quasi-conformal extension is not conformal only in this strip. However, for real part of z less than -1 over alpha, it is actually linear. So this quasi-conformal piece is just an interpolation between h and its linear part at infinity. So already sounds interesting. Well, now if I still have some time, yes, if I still have some time, I would like to explain one application of this condition of the Becker's construction.
Okay, sure.
Yes. Okay. So thank you. There are many sharp estimates which are known for the class S, for the whole class S. So when we consider all univariant functions in the unidisk normalized by this expansion, saying basically that f is tangent to the identity at the origin. Well, one famous example is, of course, the Debranche result, that the maximum of the nth coefficient, absolute value of the nth coefficient, is equal to n for all n greater or equal than. This was conjectured by Ludwig Bieberbach in 1916, and since then, in this period between 1916 and 1984, it was a huge hunting company for all kinds of sharp estimates in the class S. So there are many results. However, also in some subclasses, for example, for bounded univariant functions. Well, much less is known for these classes Sk, where we have the additional condition that F has a K quasi-conformal extension with a fixed point at infinity. Well, I think that this list, which I made here, is almost complete, but I cannot be completely sure, but this is what I know. To my best knowledge, the only sharp bound known for absolute value of Taylor coefficients is that the maximum of A2 in Sk equals 2K, and it's a rather old result. Then there is a sharp upper bound for the Schwarzschild, so it's sharp for all points Z in the unit disk. Yes, it's also old result proved independently by Kuhnau and Lehto. I'm not sure about the pre-Schwarzschild. There is an estimate, but I'm not sure that whether it's sharp or not. Well, there is also sharp form of growth theorem, so the estimate for the absolute value of at a given point. And the estimate is rather complicated, but it was found by Gutliansky in 1978. Also, many estimates, almost every estimate in the class S, it generates by the so-called majorization principle. Due to Lehto, it generates an estimate for the same functional in the class Sk, but in most of the cases, what we get is not sharp. In 1977, Kuhnau and Niske posed the following question. They asked whether it is true that the maximum of the absolute value of the third Taylor coefficient in the class Sk equals K for all K sufficiently small. Let's say for all K less than certain positive K naught. Well, the fact that this maximum is at least K follows from an example. So this function written here, it belongs to Sk, and its third coefficient equals exactly K. So here, our answer to this question, that's a theorem from a joint paper with A.K. Hotter, which is going to appear in the proceedings of the IMS. So we found the maximum of the absolute value of A3, not in the whole class Sk, but in its subclass admitting Becker K quasi-conformal extensions. And as you can see, this maximum is strictly greater than K. So the answer to the question is, of course, negative. Well, there is still small question whether in the whole class, okay, small or big question, whether in the whole class Sk we have the same maximum. Well, the answer is no. Actually, we were able to show that the two functions which are extremal, for which this maximum is achieved, they are not extremal in the whole class Sk. So, nevertheless, to answer this question, it was enough to consider a subclass. Yes, probably I should mention this, that previously there was published a result by Samuel Kruskal, and from his result it follows that the answer is actually positive. So there should be something wrong there, because in our case we have basically almost explicit example. I cannot write the formula for the function I was not able to write a formula for this function, explicit formula for this function, but I can write the corresponding Beltrami coefficient and the corresponding Herglotz function, and it is possible to calculate the first Taylor coefficients A2 and A3 of this function using the Herglotz function. So it's just work of some trivial integrating a system of differential equations. Yes, and probably the last important message in this talk is thank you very much for your attention.
Thank you. Okay, we're a bit over time, but maybe there is time for a question or for a comment or for. Any other questions? Okay, if there are no questions, I cannot see the. Oh, I cannot see the chat. That's why. Maybe I can't see if there are comments.
No, they're not.
Oh, they're not. Okay. Okay. So let's thank Pavel again and for the next seminar.